Hello students, welcome back. As the final topic on lesson 4, we're going to prove the law of sines and the law of cosines. If time permitting, we'll prove the rule of cosines as well. First, the law of sines. Let's begin with a triangle like this, an acute triangle like this, which is a bit easier. We'll consider the obtuse case a bit later. The key point is to decompose this given triangle into two pieces, two right triangles like this. So draw a perpendicular line like this and call this height as h. And what you see, you have a two right triangle, A, C, and this point, I don't know, let's call it, say, R. And then another right triangle, ARB. And then, with respect to the angle C here, this H is opposite and B is hypotenuse. With respect to this angle B, H is opposite and C is hypotenuse. Opposite of hypotenuse is sine, so sine of C and sine of B are both related to this common height h. That's the setup. Let's begin. First, decompose the given triangle into two right triangles like this, blue and red. And then forget about this A for the time being. Let's consider B and H. With respect to the angle C, what is this? Sine of C is opposite of hypotenuse, so H of B, therefore H is B sine of C. That's coming from the blue triangle. Now let's do the same for the red right triangle. Sine of B is opposite of hypotenuse, H over C, therefore H is C sine of B. So H is B sine of C, and that's equal to C sine of B. So these two must be equal to each other. Yeah, as you can see here, setting these two equal. They're both equal to H. So B sine of C, C sine of B, they're equal to each other. Setting up these are equal. All right, and then divide both by B times C, we get the desired result. Sine of capital C over small c equals the sine of capital B over small b. Alright, we have one equality here, and repeat the same process with respect to the other angles, and you're going to get this equality, and the other equality, the other two, and so on. So that's the proof of the law of sines when the starting triangle is an acute triangle. What if we have an obtuse triangle? Will that cause a lot of difficulty? Not really, as a matter of fact, because sine of C, the obtuse angle here, is not different from sine of C on the other side. Remember, sine of pi minus C, sine of pi minus C is same as sine of C. Or you can consider this as the origin, and then x-axis horizontal, y-axis not there, but you can imagine that. And then this is the radius, and we have a point here. Vertical, y-coordinate, is h, and radius, the distance from the origin, is b. So h of b is sine of c, and h is b sine of c, same as before. Whether you look at this blue triangle or consider an coordinate axis, either way we get the same thing. H is B sine of C. And as for angle capital B, that's easy. We are looking at this ARB, the big right triangle. So same kind of argument, opposite over hypotenuse. Or if you prefer, the vertical over radius. Either way, we have sine of capital B. So kind of sine of capital C here, and the C sine of capital B here, these two are the same h. setting them equal and divide by BC, we get what we want. And then repeat the same process with the other angles, we get the desired result. The ratio is all the same, and that's a law of sines. Okay, the proof of the law of sines wasn't too difficult. Now, the proof of the law of cosine, this one is going to be difficult. Okay, so what do we have here? Let's consider this one here. Okay, all right. Again, the idea is, I think I did this one here. Okay, the idea here is going to be similar. So, just like last time, we draw a perpendicular line here and name this point, say, capital R. And then the distance here, C to R, this one here, which I'm going to name it as X. And this one here, which I'm going to name as Y. Then what do you get? X plus Y add up to... Oh, wait a minute. X plus Y adding up to Y. That's for the rule of cosines. No, excuse me. That's not the key point here. The key point is this. Hypotenuse B squared is X squared, horizontal squared, plus vertical squared, H squared. Yeah, that's the key point. The Pythagorean theorem. H. And then, let's make this observation. In place of X, I'm going to plug in A minus Y. Does it help? I mean, am I simply making the Pythagorean theorem into something particularly most complicated? How will this thing help? Amazingly, it does help. Let me show you. Let's begin. Okay, here we go. So let's look at this blue right triangle. AC, the hypotenuse squared is AR, horizontal squared plus, AR is vertical squared and CR is horizontal squared. So B squared is H squared, so vertical squared, plus, instead of CR, entire BCA minus BR, this one. Alright? Will this help? I mean, changing this CR into A minus BR, I just made it unnecessarily complicated. Will it help? Amazingly, it does. Because if I now look at the red right triangle, this BR can be expressed as C cosine of B. Yeah, cosine of B is adjacent to the hypotenuse, so BR can be written as C cosine of B. Hypotenuse is C. And H here can be written as C sine of B. Again, look at this red triangle, right triangle. H over C, vertical over hypotenuse, is sine of B. BR, the horizontal over hypotenuse, is cosine of B. So we have BR as C cosine of B. This one here, which I'm highlighting in green right now, goes right here. And H is C sine of B, which I just highlighted in purple, goes right here. Alright? So after substituting those, this is what we get. So Pythagorean, AR squared plus CR squared, vertical squared plus horizontal squared, AR squared is H, alright? And that's C sine of B, alright? This purple, okay, purple, alright? That came from sine vertical over hypotenuse. Now, how about this horizontal CR squared? Re-expresses as A minus BR. Weird. But use trigonometry. BR is C cosine of B. Horizontal over hypotenuse is cosine. So re-express like this, C cosine of B here. Once we get to this point, it's not that bad from this point on. Just apply some routine algebra. Break up those parentheses using the complete square formula. And then remember the formula number 1. Sine squared plus cosine squared add up to 1. We end up with this computation. We got up to the third line and break up. What do you get? A squared minus 2ca cosine of b plus c squared cosine squared. But this cosine squared, sine squared add up to 1, so we get c squared. And then we got a squared here, and then minus 2ca cosine of b. Isn't that precisely what we wanted all along? Trickier, but it works out. Now, what if we have an obtuse triangle? Similar argument works, a little bit more complicated. Let's see, in similar kind of argument, let's look at this blue right triangle. B squared, that's hypotenuse squared, is vertical squared, h squared, plus horizontal squared, cr squared. But cr squared can be considered BR, the total, minus A. So previously we had A minus BR, this time's BR minus A. Previously, A minus BR, but this time BR minus A. Is that a problem? No, not really, because we're going to square it anyway. And then look at this big right triangle. Use the same kind of trigonometry, then we get BR. The horizontal is C cosine of B. And height, h, as c sine of b. So we can plug those in, and then we're going to get this result in the end. Vertical, c sine of b squared. Horizontal, c cosine of b minus a squared. Once you get to this point, it's not too bad. Break up the parentheses, and then apply Pythagorean identity, sine squared plus cosine squared equals to 1. Then we have these two, we had just c squared, and what's left is precisely what we want. So we proved the law of cosines for both acute and obtuse triangles, and we can repeat the same process to the other angles as well. Now, do we have enough time for the rule of cosines? A is b cosine of c plus c cosine of b, and likewise we have 3 identities here, 1 for each side. The idea is this: decompose, and a is cr plus br. Yeah, these distances add up to a. And use the trigonometry from this blue triangle. C cosine of b is cr. And b cosine of c is br from blue right triangle and red right triangle. And add up, we're going to get a. So a is c cosine of b plus b cosine of c. So lowercase, uppercase, lowercase, uppercase. Repeat the same process with the other angles. We're going to get the rule of cosines. But I don't know about this, because in terms of application, it's far less useful. I don't really use rule of cosines very often, and our textbook author doesn't really deal with this one either. And a special case when C is obtuse, a bit trickier. We have to consider subtraction, the big triangle minus this blue. But then again, cosine of pi minus c turns out to be negative cosine. So in the end, we retrieve this plus. So in the end, we get the same thing, the rule of cosines. That completes the proof of everything except Heron's formula, which I'm skipping.